everyone and welcome back to my channel. In this video, you're going to review ordinary differential equation skills, which are going to be used in partial differential equations class. So this video is for people who are going into partial differential equations class now, or are retaking ordinary differential equations class because it's a hard class and it is common for people to have to retake it for different reasons. So this is not for people who are for the very first time learning how to solve any of these differential equations, okay? So this is not a way to learn it for the very first time. All right, so I'm going to start solving using different techniques. And number one will be separation of variables. Number two, integrating factor. And it'll be second order differential equation with constant, so numbers as coefficients. Number four will be functions as coefficients, so Cauchy-Euler. And number five will be non-homogeneous differential equations, okay? So obviously the differential equations that you're going to see in ordinary differential equations class are going to be necessarily solvable using these skills or these techniques. So there are so many other differential equations that are not solved using these techniques, but those you will simply not see in your books, right? So the only integrals and only differential equations that are solvable using these elementary techniques are going to be found in your books. So these skills will totally suffice to get you through the ordinary differential equations class. So the first and the best technique, because it's the easiest technique, is separation of variables. And it is what it says it will be. You're mechanically separating variables. It's very similar to having your food not touch on your plate. So your y variables are going to be on the one side of the equal sign and your x variables on the other side. So if you can mechanically do this, like I did here, I moved this over here and I put integration signs on both sides. And after I've done this step, then it's just calculus. And this is y, and you can write out explicitly what y equals to get your final answer. But sometimes leaving it here is better for different reasons. Okay, so the second, if the separation of variables doesn't work, the second technique is integrating factor. So this is what you try. You take this function, whatever is in front of the y there, and then you put that here, and you take the integral and put that as an exponent of e, and you multiply every single thing that you have in the original differential equation by this integrating factor. Okay, just like I did here. So everything is multiplied by e raised to negative 2x. And what happens with integrating factorable differential equation is that on the left side, you're going to have a product rule. And product rule of what? So there's one type of a function multiplied by another type of a function, and its derivative is being taken. So you can collapse that and write it as, okay, this function times that function, derivative of that. And if you expand it, or if you take derivative of this function and this function, you will get what you have on the left side. So this is obviously same as this. This is the only reason I can make that substitution. You just collapse version, and this is just expanded version. So you want to be able to write the left side collapsed in this way, because the next thing that I will do is put the integration sign, and we know that integration and differentiation are opposite operations. So if you're integrating something and then taking derivative of that thing, you're basically not doing anything. So might as well cancel them out and not start that circular process. So that's exactly what you are doing integrating factor for. So the right side, you just do a simple addition of the exponents and you get e of x here. So both sides have integral, and these get canceled because you have differential there as well. And here, it's the simplest integral that we know how to take. It's itself, right? So, and plus constant of integration. And you can take this on the other side so that you can have a y separately, and this is your final answer. That was integrating factor. Now, version 3 is a second order differential equation with constant coefficients. So here you have 1, here you have -5, here you have 6. And you're taught to just rewrite that as a quadratic equation. And the reason you're really doing that is because you are hypothesizing that a certain function would have solved this. And then you go down that train of thought, and then you end up with this quadratic equation. I will show you what you're doing in effect, because that is what you're going to do with Cauchy-Euler. But here it's kind of taught like, just rewrite this as a quadratic equation. But really what you're doing is like, with differential equations, the task is to find a function whose, this is the story, right? Whose second derivative minus 5 times first derivative plus 6 times the function itself will equal to 0. What is that function? There's y of x such that if you do this, then that will be the differential equation. So you're after the function. So you're gonna hypothesize that I think the function will have this form. More often than not, this will be the form, right? So this is what we're gonna try out. But if this is like your very first time, then if you try out different forms of functions and you take second derivative minus 5 times first derivative plus 6 times this form itself, I mean, at some point you're going to get the function that will work. But right now we're going to try something which is a pretty good try to begin with, because we've done enough of this and we can look ahead and know what function makes sense to try. So if I tried this, then what do I need? I need first derivative, second derivative, and I got expressions for those. And I'm going to take second derivative minus 5 times first derivative plus 6 times the original function that I'm trying out, which is this. All right, so if I do that, then I'm going to be able to factor this out. And if I factor it out, then I'm left with this expression, which you're taught to write immediately after you see this sort of a ordinary differential equation. And the reason why this is the only thing that matters is because you know that this can't be 0. And what you have here is that one expression is multiplied by another expression. Its product is 0, so one of them has to be 0. Well, this can't be 0, so then this has to be. So now we're going to solve the quadratic equation. And when you're solving quadratic equation, you're hoping you're not going to have complex roots, right? Even in high school, that's always nice. And here you're also hoping you will have distinct roots. That's the best or the easiest. Here it ended up that we did, because I set it up in that way. I will have the complex root version down with Cauchy-Euler so that you can see the worst of it. But here we have the best of it. So we have 2 distinct roots. And since we have distinct roots, we need a linear combination of what we tried out to begin with. So we tried out this form right here. So I got u1 equals to 2 and u2 equals to 3. So I'm just going to do a linear combination of the two. So this is my final answer. Okay, so the reason I'm doing a linear combination is because what is linear? The necessary requirement of linear expression is that it is closed under addition and scalar multiplication. So you just add terms and that's totally allowed. Okay, and here's a reason why we need 2 of them explained there. So this is the second order differential equation. Now, instead of constants, I have functions as my coefficients. So this is where we're going to use Cauchy-Euler. So I wrote out the coefficients. First one in front of the second derivative, I have x squared. Then I have linear x, negative 3x, so x is raised to the first power. And then I have x raised to the 0th power, or simply no x there, right? So I'm seeing a lot of x's with some different powers. So the function I'm going to try out, do you see the process is the same as it was in the constant coefficient second order differential equation? So you're trying out a function that you think will solve this differential equation. And then you follow that thought and see where it leads you. Here I'm going to try x raised to m power because I see a lot of x powers and I'm hoping I can factor something out. So this is what I'm going to try. So, and I have written out why I'm trying that. So, okay, so then I'm going to follow the recipe. So this is the differential equation, the original differential equation. I need second derivative, I need first derivative, and I need the original function. This is the original function I'm trying out. This is its first derivative, and this is its second derivative. And I don't forget to multiply second derivative with x squared, then negative 3x times first derivative plus 3, it's the original function itself. And here I recognize that there's x raised to the second power and x raised to m minus 2. And I add these and I get rid of 2. So I have x raised to m. Here I have x to the first power. That cancels here because you add the exponents because they have the same base x. Here, let's just leave how it is. And x raised to the mth power is, we're able to factor that. So since I'm able to factor this, then I'm left with this expression. And with Cauchy-Euler, usually you are given some sort of, okay, x is more than 0. If x is more than 0, I know that this right here is not going to be 0, so that this other expression has to be 0. So I will just work on this. I will simplify it, do simple algebra on it, and I will get a quadratic equation. Okay, again, I ended up with a nice version, 2 distinct real roots, okay? So I will simply say that since I tried out x raised to m and I have 2 different distinct roots, I will have to do the linear combination of both of them. So one is 1 and the other one was 3, so I will do, again, linear combination, this plus that version. Now, if I had, instead of the original equation, which had minus here, if I had plus there, then I would have the same exact thing up until here. I would still be able to factor out x raised to m, which again can't be 0 because that condition would still be there. But then I would have, instead of this quadratic equation, which has real roots and distinct at that, this will not have real roots because I will end up with square root of negative number, negative 8. So I will end up having m1 and m2 both being complex numbers. So then I will have to use this form, right? This is the general form. And in my case, alpha is -1, so I will write it like so. Now, the only weird thing here should be this ln x that might be surprising to you, and I will explain where that comes from here. So remember that what we were trying out as a function that will solve initial differential equation, second order differential equation, was this. Well, now I'm just looking for m's, and my m in this case ended up being complex. So, okay, I just write that x raised to m, it happens to be complex, so I write that as a power of x. Now I will separate them. I will have x raised to -1 times x raised to I square root of 2. So then I will write this x raised to the I square root of 2 as this. And the reason why I can do that is because with any number, let's say a, raised to another number b, you can write that as this exponent comes as a coefficient there times ln a. And then you can always put this back here, and in that case, e and ln will cancel each other, and you will get back your a raised to b. So you can write any number raised to another number in this form. It would be odd, but mathematically correct. So I'm going to do exactly that to this expression. So I'm going to bring this in front, the exponent. I'm going to put e, bring this exponent in front, and have ln x. And I can always put this back, and ln and e will cancel each other, and I will get this back. So I'm not violating any math rules. Now, since I've written this as e to the power of I square root of 2 ln x, now I can use Euler's formula. Remember, e ix equals to cosine x plus I sine x. And in my case, it's just square root of 2 ln x instead of x, right? This whole thing is the argument. So this is my Euler's formula. And this is how ln x ended up here, right? Instead of just x. So that was the explanation for that. Now, non-homogeneous version. This is not very difficult. Sometimes you have homogeneous, sometimes non-homogeneous. So this could be on this side of the equal sign, and then it could be 0. So don't look for 0 on the right side. Just look for expressions with x. So here we have one. It could be on either side of the equal sign. So don't remember that it has to equal 0 for it to be homogeneous, because I could have written it like this and it still wouldn't be homogeneous. Okay, so the rule is to first solve homogeneous version of this. So pretend this is 0. Solve this equation, get the homogeneous solution, and then try out the function that you have here, f of x, here equals cosine x, and try out function that will solve that. So basically cosine x. Unless you have cosine x or sine x in the homogeneous solution, then multiply your particular solution by x and try that out. So you can't have repeats between particular and your homogeneous solution, because you need linearly independent terms in your solution. So here is a little quick rule of thumb, how you choose what you're going to try for your particular. So if you have polynomial, you try polynomial. If you have e raised to some number times x, you try this. If you have cosine or sine, you try a times cosine bx plus b sine bx. Okay? So if your trial duplicates any of the terms in your homogeneous, then multiply your trial by x. When in doubt, when you have like duplicates, just multiply your trial by x. And if you also have like x times cosine x, then multiply it by another x, so x squared or x cubed, right? And then you won't have duplicates. And so you'll be fine with linearly independent requirement of your answer. So first we solve homogeneous, and this is the solution for your homogeneous. We ended up with complex number. Alpha was 0, and this is the general solution. This is our particular solution. So we have homogeneous solution. Now let's work on the non-homogeneous solution. So particular solution, I'm going to multiply what I was going to try otherwise if I didn't have the duplicates between homogeneous and particular. I'm going to multiply that expression by x. And then I'm going to just follow the recipe. I'm going to get second derivative, but I need first derivative. I don't need it for the equation. I just need it first derivative to get to my second derivative. So this is just a transitionary step. So the second derivative was this expression right here, and I write that instead of my y double prime p plus yp, and that equals to cosine x. Things get canceled. If they don't, you've tried a wrong thing and you've taken wrong derivatives. And here I ended up with this expression. I don't see signs on the right side, so that tells me that a must be 0. So I write that down, that a is 0, because you're going to need that. And then 2b, you just match. This is called the matching step. So you just match the coefficients. So 2b equals to 1. There is no other cosine term on the right, so that has to be 1. Therefore, b is 1/2. Now you take the y particular, not with derivatives, just to the original version of particular y, and you have a in front of cosine. So that's 0. And then b is in front of sine, and that was 1/2. So this is your particular solution right here. And your general solution is going to be linear combination, simply addition of your homogeneous solution, which was this right here, and your particular solution, which is this right here. And this together is your final answer. Okay? So here's some other problems for your additional review. I will have this document linked in the description box, so you can maybe solve these and check yourself. I have everything written out. With this, the homogeneous solution will include one of the e to the 2x. So you have to multiply your non-homogeneous particular y by x and try that out. Here, you're good to go because homogeneous won't have e raised to x. Okay, this one is Cauchy-Euler, but I have written everything out, so just follow that, and that will be a great review for your partial differential equations class. Or if you're retaking ODE, then you can be slightly more prepared. Thank you so much for watching. Bye.